Hello, Daniel Payne here, and welcome back to the Seller Lesson production for its first and only episode. Today we're going to be covering problem set 39, question 4, which entails a train going from Boston to Washington, D.C. on a chord line between the Earth and finding the travel time between these two, aka half of the period. So, I drew this nice little diagram to the right over here, which entails of radius of the Earth, a radius just of the chord to the chord line, and then a y in that, a y distance to the chord line, which will be constant, an x distance, which is also variable, and a variable theta. So first off, let's just start simple. Let's find the force of gravity applied to this train on the chord line. So first, just force of gravity equation is Fg is big G, mass of Earth, times mass of train, over r squared. However, this train is going throughout the Earth. And this means that while this equation would work any place outside of here, like even on the border, even if it was just like right on the edge here, it would work just fine. However, say it's right here, where just like the example is drawn, there's all this mass outside of this is not applying to the force of gravity in this case. So we need to find a way to get rid of this. And how we're able to do that is we can multiply it by the proportion little r over big R, as this will only get the proportion of mass that actually is affecting it, aka like the mass of the volume inside of the radius due to wherever the train is on that chord. So this will give us the equation negative g times big M times little m over r cubed times r. Sorry, big R cubed times little r. So now that we have this, we need to start finding the force in the x direction here. We're looking for the period that's going to be happening in the horizontal, so we need to find the horizontal force. Makes sense. So we have f of x equals fg times sine of this nice little theta value I already drew in. And using that theta value, sine of theta, we already know that this is going to be x over r. So we'll just rewrite that, fg equals x over r. And if we plug in this equation right here, we're going to be getting negative g big M little m over r cubed times x. So now that we have this, we need to start figuring out how do we apply this to time. We got a force in the x direction. We can look at the green packet and we get this really, really nice equation and going along with this hint, we are able to apply something really nice. We know the equation ax equals negative omega squared x. Random equation, but it works so well. Because now if we take this equation right here and apply it and put it in and substitute for the a of x, we get that equals d squared x dt squared minus gm big M over r cubed times x equals this. That's a multiple. And now that we have this, we know that the frequency, this is angular frequency in this case, we know this squared equals big GM over r cubed. And this omega squared is really big because in finding the period, now that we know this, we're able to find the period really easily, just going off the equation that we've been using for pendulums and springs all year. T equals 2 pi times inverse of omega. So now we have this, we have omega squared, angular frequency. So that's going to be square root of gm over r cubed. Plug it in here, you get t equals 2 pi square root r cubed over gm. And this is something we have all the values for. And we can start plugging things in. So start plugging everything in. You get 2 times pi, pretty simple, over our radius of the Earth. If I remember, Doesn't give you, so you just have to look this one up, but 6.3 times 10 to the 6th, and this is going to be cubed, over gravitational constant. You can look that up on your green packet. Actually, yeah, green packet, maybe the blue packet. Multiply this by the mass of the Earth. Also, it doesn't give, but luckily the internet exists. So you do that, plug this all in, and you get 84.2 minutes. So you found the period. But one quick thing, don't forget, period is going to be saying this to there and back. You're talking about here, going back, and now returning to its original place. But it doesn't ask for that. It asks for the city-to-city travel time, right there. City-to-city travel time. It doesn't want the city back to its own city. It wants to know from here to there. So all that means, pretty simple. Like I said in the beginning, just going to divide this whole thing by 2. And our delta time, total travel time, is going to be 42.1 minutes. And there's your answer. Anyways, thank you for the one and only episode and listening to it of the Stellar Lesson Production. Hope this helped, and have a great rest of your day.